Have you ever wished a machine could just tell you it's about to break down before it actually does? Well, today we're diving into a really cool piece of research that does exactly that. We're going to break down how a new parallel AI model can literally listen for the faintest whispers of an impending failure and predict it way ahead of time. So here's our game plan. First, we'll uncover the tiny, unseen culprit behind massive machine failures. Then, we'll see how AI is coming to the rescue. After that, we'll explore a very clever two-pronged attack on the problem, look at the pretty amazing results, and finally wrap up with why this all matters for the future of intelligent machines. Okay, let's get into it. In our super automated world, everything from our power grids to high-speed trains, it all relies on huge, complex machinery. But what if I told you that the biggest, most catastrophic breakdowns often start with the smallest, most overlooked little problems? Think about it for a second. What do all of these gigantic, powerful pieces of tech have in common? They are all completely dependent on one surprisingly small and honestly often forgotten component to work flawlessly. And the answer is the bearing. It's the unsung hero tucked away inside almost every machine that spins or rotates. And yeah, it might be small, but its job is absolutely massive. It's really the silent workhorse that keeps our entire world moving. So what do they actually do? Well, bearings are the reason parts can move smoothly against each other, cutting down on friction and wear and tear. But here's the catch. When a bearing develops even a microscopic little fault, it can trigger a devastating chain reaction, leading to catastrophic, super expensive, and sometimes really dangerous equipment failure. So how in the world do you catch these tiny little faults before they turn into huge disasters? Well, the answer lies in listening very, very carefully, with a little help from artificial intelligence. Think of it like this. Every machine has a unique vibrational signature, almost like a fingerprint or a heartbeat. As a fault starts to develop in a bearing, that signature changes in these subtle ways that a human would just never be able to detect. But a deep learning model, it can be trained to listen to this vibration data and spot those telltale signs of trouble long before we can. And hey, this isn't just some neat party trick. The researchers behind this model said it best. This kind of intelligent diagnosis is absolutely fundamental if we want to build the next generation of smart, automated machinery. But how does this all work in practice? Well, this is where things get really clever. The researchers didn't just use one AI. They built a system that attacks the problem from two completely different angles at the exact same time. Here's a bird's eye view of the whole process. It all kicks off with the raw vibration signal from the machine. That signal then gets converted, split up, and analyzed in parallel by two different kinds of AI. And finally, their results are fused back together for one single, super accurate diagnosis. Now this right here, this is the secret sauce. The system takes that raw vibration data, which is basically a one-dimensional wave over time, and transforms it into a two-dimensional image. Imagine turning a sound wave into a detailed picture that actually shows you its pitch and rhythm over time. This one simple step unlocks a whole new way to see what's going on. This slide really brings that two-pronged attack to life. On one path, you've got an LSTM model. Now, that's an AI that's fantastic at understanding sequences over time. So it's basically listening for the rhythm of the fault in that original signal. Then on the other path, you have a CNN model, an AI that's a pro at image recognition, analyzing that 2D picture we just made, looking for specific visual patterns that scream problem. It's like having two different experts, a musician and a painter, both analyzing the same piece of information. So, the big question, right? Does this whole two-pronged approach actually work any better? Let's take a look at the data. And the researchers didn't cut any corners here. They really put this thing through its paces, testing it on two different public data sets, running it under all sorts of conditions to make sure it was not only accurate, but also tough enough for the real world. And the results? They are staggering. The model achieved a diagnostic accuracy of over 99%. Let that sink in. That means it could correctly identify the health of a bearing, whether it was perfectly fine or had a specific kind of fault almost perfectly, every single time. And this chart right here is exactly why that parallel approach is so powerful. Look, on their own, the LSTM and CNN models do a pretty good job, 85 to 92% accuracy. But when you combine them, their strengths cover for each other's weaknesses, and the accuracy just skyrockets to a near-perfect 99.5%. It's a classic case of the whole being way, way greater than the sum of its parts. So, what does all of this actually mean? This is way more than just an interesting academic exercise. This kind of technology has really profound implications for how we build, how we maintain, and how we interact with all the machines that power our world. When you boil it all down, the takeaways here are huge. This tech lets us move from being reactive to being predictive, fixing problems before they even cause a failure. That means less costly downtime, much safer automated systems, and it gives us a blueprint for even smarter diagnostic tools in the future. It really gets you thinking, doesn't it? If we can train an AI to hear the future failure of one single tiny component, what other invisible problems could it learn to detect? What else can it see coming that we can't? Thanks so much for tuning in.